thank you for coming. If you have questions, like we have 2 microphones, so feel free to step to the microphone, raise your hand, make some noise, and I'll be happy to try to clarify. Automotive and IoT exploit. Sounds exciting, doesn't it? So who am I? Who has ever heard about me? Wow, that's almost everybody. Okay, I'm mostly famous for sort of making hardware backdooring, something theoretical to something practical. That's something I demoed at Black Hat and DEF CON 10 years ago. Like, we knew firmware was somewhat vulnerable to attacks, but I presented an attack, a proof of concept malware called RSA, which infected 300 different motherboards. So that came from like, maybe it's possible to, that's definitely possible. And nowadays, that's a world field of expertise. So if you Google for hardware backdooring, or if you look at like the Wikipedia page for it, like the first reference is going to be my work. I've been working on like low-level security for like 15 years, something like this. I authored the 16th advisory ever at Intel, and that was a cool one. That was breaking all the BIOSes on the planet with a single exploit. So that worked against BitLocker, which is the full disk encryption for Microsoft, against most BIOSes on the planet, as well as like most full disk encryption, like whether you use it like McAfee endpoint or like the open source alternatives like TrueCrypt. So if it's not entirely clear, I'm French. If you don't understand what I'm saying, feel free to ask me to repeat. Maybe it's not just you. So after living in France, I moved to India and then to Australia. And I've been living here for 6 or 7 years now, when a small company in town called Salesforce asked me to be one of their directors for security. So I started as product security, and then I moved into offensive security, which is essentially red teaming and security research. So I spoke at Black Hat a number of times, at DEF CON a number of times. I helped run a number of conferences. I used to run one in France called No Such Con. And I helped on the advisory board of the cool conferences, one in Goa called NullCon, and one in Hawaii called ShakaCon. So if you happen to run a cool conference and you need board members, well, it has to be in a cool location. Otherwise, I'm not interested. I'm a PhD candidate in Paris at the CNAM. And yeah, I hold a master's degree in engineering and one in artificial intelligence. We don't really care about this today, but we're going to talk about like very cool stuff if you're into IoT, so industrial Internet of Things, which is like the next generation of connecting plants and connecting like supply chains. There's obviously a whole lot of benefits to do this. From a security standpoint, it triggers a number of like very interesting process problems. So I'm the CEO of Moabi, which is a company that tries to help very large companies better their SSDLC. We're strong believers in the fact that security is not a product, it's a process. Paraphrasing Bruce Schneier. So what we try to do essentially is imagine you like a car manufacturer and you want to do update over the air for your cars. So you want to, push software to your cars, and you want to do this like on a monthly basis maybe. And before you push this firmware to these devices, you'd like to have some kind of check, which is both hardcore reverse engineering and kind of new in terms of process integration. So that's what we do. We built a cool tool which allows to do, like you upload a firmware on it, and it computes a number of metrics, which are like legacy, hardening, cryptography, compliance, and look for vulnerabilities and 0 days, as well as like existing CVEs. And the whole challenge is like, how can you find 0 days automatically out of a binary without access to the source code? So to do this, we use both what's called static analysis as well as symbolic execution. Anybody's familiar with symbolic execution? Yeah. So basically, it's a whole set of like new technology, which is for the time being, mostly an academic field of research. And the problem with this, if you're familiar with SAT solvers like Minisat and things like this, is that it's an exponential problem. So what we managed to do is to strip that down to something which is polynomial, so we can do that in reasonable time. To give you an example of what we do is, my first customer was Renault, Nissan, Mitsubishi, which is like one of the largest car manufacturers in the world. They're competing with essentially Honda and Volkswagen to be like the largest car manufacturers in the world. I know we're in San Francisco, and everybody's like, yeah, Tesla's cool. All right, so if you take all the Teslas in the world ever shipped, that's 1 million cars. Those guys ship 10 million cars a year. So Tesla is like famous in Soma, and those guys are the big deal in the rest of the world. So what we do is basically help those people before they do an upgrade, like verify the quality of the software they're pushing. Anybody who's working in the car industry? Yeah, I know oh, wow. Okay, we're not in Michigan, but for the rest of the people, the big challenge with the car industry is that basically, if you take a car, 70% of the software is not written by the car manufacturer. It's coming from open source, and it's aggregated through like tier 1 and tier 2 suppliers, them being like, Bosch or Denso or RSA or whatever. And those people take all those open source software, compile them, bundle them, give them to the car manufacturer as binaries only. So that's the challenge. If you give me the source code, it's obviously a lot easier. But if you just give me the binary, can we actually say something before you push that to the cars? So that's the product we wrote. All right, so as part of an audit for one of my clients, we looked at what's called Genie IVI, which is essentially, if you take a car, it has like about a dozen, maybe a little more, depending on like the range of the car, computers in it. There's called ICUs. And the IVI is essentially the entertainment software for the car. So Genie IVI is like a consortium of like a number of car manufacturers who came together and were like, hey, how about we do something open source that people can customize and reuse? And that's the root of like the entertainment system for many, many cars in the world. So we're talking, I told you one car manufacturer is shipping around 10 million cars a year. So you take like all those big car manufacturers, that's many, many million cars a year. Cool? That's what we're going to talk about. So we run an audit of like the entire firmware of Genie IVI for this client. You can see like on the top left corner, that if you take the entire firmware, what is the rating of those binaries? So those on the right, 100% rating. That means that they don't have a problem. But the queue of the distribution shows that, well, it's not entirely perfect. And if we look at like the vulnerabilities found, on the bottom left, we can see that they have some hardening problem. What's hardening, by the way? Okay, so hardening a binary, it's like compiling it so that it's more resilient to attacks. So we can use technologies like ASLR, which stands for Address Space Layout Randomization, meaning every time you run a program, it runs at a different address in memory, making it harder for people to exploit it. If there is, say, a buffer overflow, you cannot hardcode the offset at which to return. It involves technologies like stack cookies. Who's familiar with stack cookies? 2 people? Okay. So that means basically you can instrument function calls so that if there is any type of stack overflows, there is a canary put there by the compiler. And if a buffer overflow happens, it will be detected instead of being Ben exploitable. So what we see here on the bottom left is that most binaries are also compiled properly, but some of them, there's like a trail in the distribution, and those are not protected properly. On the bottom right, we can see that we detected a number of buffer overflows, arbitrary file creation, well, a number of problems in this particular Genie IVI firmware, which is extremely popular. Like if you have a car, the entertainment system is quite likely a derivative of this. So a particular binary which attracted our attention was hostapd. So hostapd is the big deal when it comes to cool binaries to attack. Essentially, if you want to turn a Linux or an IoT software into a Wi-Fi access point, there's essentially one software to do this in the world, and that's hostapd. So if we find 0 days in hostapd, we owning billions of IoT devices. I told you about your cars, but your home router, for instance, which is allowing you to connect your phone or your laptop to the internet, is extremely likely to run hostapd internally. And if we look at this particular binary, so we see that the hardening is not great, which means if there is a vulnerability in it, it's quite likely to be exploitable. Compliance is fine. There are some cryptographic problems, but mostly there's a bunch of vulnerabilities in it. And I'm going to describe you one, which is really cool, or rather two, which are really cool. We reported those vulnerabilities to the CERT about a year ago, but it's the first time I'm presenting them in public today. All right, so the static analysis of our tool came with this. CWE 330, insufficient use of random values. What is this? Who's familiar with a PRNG? Pseudo-random number generator. Okay, that's about half the people who are developers. So it means when you need random numbers on a computer, well, that's difficult. So what we use is called pseudo-random number generators, which are sequences of numbers which look random, and you start at a given period in the sequence. The problem is, if you do not seed those PRNGs, they repeat forever. And I'm going to give you a demo of this. And that's usually really bad from a cryptographic perspective. So what we got here is we took the binary, we ran a static analysis on it using a bunch of modern static analysis, including symbolic execution. It came with this. And the question is, can we verify this binary is actually vulnerable? And can we craft an exploit? Any questions so far? Too easy. So I'm going to tell you about CV 2016-17043, and then there's another one called CV 2019-10064, which is the denial of service. But this one allows remote access to any hostapd-enabled device, meaning anything using Wi-Fi as an access point is vulnerable to this, which is bad. All right, so if we look at the binary itself, so I'm using a bit of magic Linux voodoo commands. What's interesting is that we take the hostapd binary, we look at all the symbols in it, and we select only those which contain the word rand. We see that it's calling functions called rand and random at the very bottom, but it's not calling srand or srandom, which are the functions used to seed this pseudo-random number generator. And that's a sign that there is a problem in them, because if you use rand or random, you are supposed to seed the pseudo-random number generator before. If you're not familiar with the problem, you can click on this link, and it will tell you a little bit more about why this is an entire class of vulnerabilities. This was fixed silently, maybe by mistake, in 2016. So that was in version 2.6, but there was no proper advisory for it, meaning a whole lot of people are not aware of this problem. And when it comes to IoT devices, there's a whole lot of IoT devices out there that just don't get updated, and there's no reason for the maintainers of those devices to actually push an emergency upgrade because they don't know there is a problem. So interestingly, we reported this to the CERT in March of 2019, so almost a year ago. But they gave us a CV number from 2016 in accordance to when the patch was issued. They backport CV numbers these days. It was not like this like 5 or 10 years ago. So that's a strong sign that, okay, there is some kind of problem here. We're going to look at that into more details into a second. So if we look at like what's happening on the right, there's a function called WPS, which is basically a standard which allows you to connect or to configure your Wi-Fi access point using a pin. There was a massive vulnerability in 2011 on this WPS standard, which showed that the entire number of pins that were supposed to be available, instead of being like many billions, was only 11,000. So somebody wrote like an exploit to brute force those 11,000 pins, and you could connect to like a Wi-Fi device running WPS in a matter of like minutes, maybe half an hour, to exhaust like the entire thing. Well, is this cool for us? It's cool for us because we don't need the we don't need to rewrite the entire protocol. What I did basically when I found this vulnerability in WPS is take the existing exploit and backport the pin numbers I know are possible into this device. And I'm going to show you in a second what the problem is. That was a cool picture, wasn't it? So if we look at the right-hand side of the screen, basically, let me show you. The bit which is interesting is over there. Right here. Oh, I think I have a pointer. Here we go. Better? Better? Yeah, the photographer should come back just to picture this. Okay, if we look at this, that looks pretty bad. So OS random, well, it's supposed to be random. It's actually calling the libc random. And that's a bit which we suspect is not seeded. So that's going to be 100% repeatable. So it's something repeatable, XOR, no sec. So that's coming from OS get type. I'm going to show you that that's coming from a libc call to get time of day. So that's basically the time of your car in seconds right now. If I'm standing next to your car and I want to connect to its Wi-Fi, because that's the whole attack, what it's all about, the time in second to your car is what? Well, it's basically the time in second on my clock. And I'm standing next to your car. So I know what the time zone is going to be. And even if you changed it in your car, it does not matter. Because if your car is less than 10 years old, it has a 3G connection, whether you like it or not, and it's synchronizing to the network. So the clock of the car, that bit, is going to be entirely predictable. And I'm going to show you another way to get it anyway. So we say that's predictable, that's predictable. We're left with like the microsecond bit of the time also coming from get time of day. That kind of look sort of random. I'm going to show you that that's actually not a whole lot of entropy. That's less than 2 bytes of entropy. So the whole WPS code to configure an access point is going to be about 2 bytes of entropy, meaning how many tries? Yeah, about 65,000. So something you can backport into the existing WPS exploit and run in a matter of minutes. I was telling you, in 2018, it would take about half an hour to brute force 11,000 of them. The Wi-Fi these days is much faster, so we can actually run that in like a minute or two. All right. So I'm going to show you. Can you please switch my screen to like. All right. So I'm going to show you a little bit. I'm not seeing what I'm doing here, so you will have to be nice with me. Okay, let's start with this. So OS 1. You guys can see this? Okay. OS 1. So we said OS random. It's basically the libc random. So we know that this is supposed to be seeded. If we look at the code, so that's the same thing as in the slides, right? I'm telling you what the value that matters is basically OS random. So we saw that's libc random. XOR, the time it is now in seconds next to your car. XOR, the microsecond. So the bit that's really difficult is this one. All right. So let's split that one by one. I'm going to show you first what random is going to look like. So that's a call. That's basically a function in C that is calling random without calling srandom first. And if we compile it and run it, or random is this, right? Okay, that's completely predictable, right? The fix, super easy, would be to, before I call rand here, to actually call srand with something which is not predictable. So don't do this. Use something better than getPID. GetPID is like the current process ID, so that's going to be different every time I run it. Good enough for a demo, but not good enough for production, right? I'm going to recompile this. And now if I run it, it's different every time. Make sense? Okay? Whoopa. So that's part of the problem we identified in hostPD. So we said the value used for the pin is not just random, it's also XOR, this thing coming from getTimeOfDay. So let's take a look at getTimeOfDay. I look a bit at like a technical example. So if we call the function getTimeOfDay, this TV argument, which is like a struct timeval, has basically two arguments. Two parts. The first one is like the time since epoch, which is like the number of seconds since 5th of January 1970 by convention. It's the age of Unix, so the age of the universe as far as like cool people are concerned. And the other bit is this thing, TV usec, which is casted to like a long integer and is the microsecond delta between epoch and the time you call getTimeOfDay. That's all right? Not talking alien here? No questions? All right. So let's run this thing. If we run it a bunch of time, what we can see is not very big, but is that predictable enough? Well, I don't know. Let's change a bit the getTimeOfDay.c so that instead of printing it as a long integer, I'm going to print it with ones and zeros. So we look if it's predictable or not. So let me recompile. And now let's run it in a loop, maybe 10 times. Okay, so I'm going to recompile it and run it 10 times in a row, but instead of printing this big number, I'm going to print it in the form of ones and zeros. And now you can see that this is not this is not random at all. Like the ones are in red, okay? They're always at the same side, the same place. The zeros are in blue, and you can see that there's clearly a pattern here, right? So that's not random. So summing it up, if we take something which is completely predictable because it's not seeded, XOR the time of your car, which I can guess because it's synchronized to the network over 3G, XOR the thing we just saw, which is predictable. The result is like there's actually a WPS pin with 2 bytes of entropy. That was evil. Can we please go back to the slides? Any questions so far? Yep. Please come to the microphone.
Sorry, you don't have to answer this if it's going to take us too far. But you showed a sequence of calls in your symbolic execution. I was wondering if that was a call stack?
That is sort of a call stack. It's like a symbolic call stack because when you're running the application symbolically, you're not actually running it like on a concrete CPU.
Sure. Forgive me. All I'm trying to understand is if it's a call stack, how do you know that it wasn't seeded at an earlier time?
How do I know it was not seeded at an earlier time? Because the binary is not linked with srand at all.
Oh, okay.
So when I hit rand, I can verify that there's no way it is linked against srand, and it's never called.
Okay,
Yeah.
Understood.
Good question.
The bit,
if you let me expand a bit further, yeah, you're right. There's a call stack here. It's when we do symbolic execution, we're not running on a concrete CPU, right? So it's actually emulating a call stack after doing like a top-bottom and a bottom-up in order to perform a taint analysis on the entire binary intra-procedural. That's a really good question. Yeah. Any other question? Too easy? So we were talking exploit prototyping. Okay, since I have a bit of time, not very much, but still, I'd like to tell you about the Witchcraft compiler, which is a cool tool I do use for prototyping exploits, and which happens to be free, open source, and you can get it from like most Linux distributions. It's a tool we presented at Black Hat and DEF CON like 4 years ago, and it's part of the repositories for like Debian, Arch Linux, Ubuntu. So if you just apt-get install WCC, you can use this tool. A lot of people use it for capture the flags and prototyping exploits. In a nutshell, the way debuggers normally work are you have a debugger who's analyzing a debuggy, which is the program you analyze. When doing so, it's extremely inefficient. If you're using the primitives called ptrace, which is the standard on Unix and Linux, there's 8 context switch just to increase one value from the debugger to the debuggy. So how does that work? You have the debugger analyzing the debuggy. First, if you want to increase one variable by 1 inside the debuggy, it works that way. The debugger has to call ptrace stop to stop the process. So that's 2 context switch. You switch into kernel land, you're coming back to user land, 2 context switch. Then you have to ptrace peak to get the value from the debuggy into the debugger. That's also 2 context switch. So that's 4 context switch this far. Then you get this value, you increment it by 1 in your memory inside your debugger, and you ptrace poke to change it inside the debuggy. So that's 2 more context switch. And then finally, you need to let the debuggy run, and you're calling ptrace count. So that's 2 more context switch. So just to increase one variable by 1 from the debugger to the debuggy, that's 8 context switch. That's absolutely terrible in terms of performance. It means if you want to do things like single stepping, which is stopping at every time there is an instruction. This is not practical. It's way too slow. So what we do with the Witchcraft compiler, where it has 3 programs in it, but the main one I'm going to show you, which is called the Witchcraft shell, you take any program you like, we patch 1 byte, we transform it into a shared library, load it into our own address space. And now the debugger and the debuggee are just one process. And if I want to increase a variable by 1, I just do it inside my own address space, and there is 0 context switch, which is much faster than 8 context switch. All right? So that's why this thing is useful and used by everybody to prototype exploits. Another thing which is cool is that you can use the JIT translation, so that's just-in-time translation from another architecture like ARM to debug on Intel without using a virtual machine. We leverage the JIT engine from QEMU, and that's amazing in terms of performance. Anybody has been using it? Never heard of it? Oh, everybody's using it? All right. Okay. To summarize what we said, I'm going to give you a demo if we have time. But to wrap up on like the pseudo number generator thing, yep, we have 20 minutes left. The big problem we have is that the pseudo random number not being seeded, it's entirely predictable. And as we saw, that's enough to reduce the address space of possible pins to just about 2 bytes of entropy, meaning 60,000, which is something we can easily brute force using existing exploits, which have been deployed for this. Conclusion, and then I go to the demos with the Witchcraft compiler, which I hope you guys use. If you're using HostAPD, which you probably are, verify you're using a version which is after version 2.6. The advisory is out. The current version should be 2.9. But since there was no advisory published when this vulnerability was silently fixed, well, there's a whole bunch of devices which are using older versions of HostAPD and possibly IoT devices that cannot be upgraded at all. So you want to check that out. In terms of SSDLC, one of the takeaways of this talk is that by using modern static analysis, things like symbolic execution, like we discussed, you can actually improve your SSDLC before you do update of firmware over the air and make sure that you actually have a check and you're not vulnerable to like known vulnerabilities or trivial vulnerabilities like this one before you push your firmware to critical devices, being it like cars, but also like, you know, we work with power plants and like medical devices, things like this, whatever your use case is. I'm also a big believer in like changing the supplier relationship management process. In the car industry, it's difficult because like we said, car manufacturers, 70% of the firmware is not written by them, but by suppliers. So having like some kind of SSDLC to make sure they actually compile things properly and that it doesn't just work is super critical. Can you switch back my screen, please? All right, let's have some fun. Any other question in the meantime? Too easy? All right, so let's do some hacking. All right, I'm going to show you, for instance, this thing. So ProFTPD is an FTP program, which is pretty popular, and it's shipped with like a number of Linux distributions. It's a normal userland program, and you're not supposed to use it as a shared library, but I'm going to show you that you can. So if I look at my version of ProFTPD, it's said to be an ELF shared object. That's because it's compiled with ASLR, so address space layout randomization. And the way we hacked this is instead, when we introduced ASLR about 7 years ago maybe, instead of recreating an entire toolchain that would allow running a program at any address in memory, we just hacked it And we allowed in kernel land execve to take a shared library instead of an ELF executable and run that. That prevented us from having to rewrite an entire toolchain to do this. The side effect of this is that you can use very much you can use this binary, which is not supposed to be a shared library. You can DL open it. So take it as if it was a shared library and call normal functions like, load it inside your own address space. So if you do something like this, that works, which is totally unexpected. We can even call functions inside it. So let's look, for instance, at this thing. So what I'm going to do is load this thing inside my own address space, look for a function called PR version getString, and print it. And amazingly, can I get back? All right, let me less this. I'm not seeing what I'm doing. Oh, okay, I'm going to do it using the witchcraft script directly. So, okay, the function we want to call is PR version getString. Somebody remember this, because I'm not going to remember. PR version getString, all right. I'm going to use the witchcraft shell to load into my own address space the proftpd binary. That's going to take a minute to load. So that's the tool which is free. You can download by running simply apt-get install wcc. And this gives you basically, this transforms any program into a shared library and exposes back into a small, tiny Lua shell all the functions that exist into this program. Why is this cool if you want a prototype exploit? Because if you have, for instance, a function main, which is calling a function A, calling a function B, calling a function C, and you suspect the function C is vulnerable, well, normally you have to craft an input that goes from main to A to B to C to be able to trigger the vulnerability in function C. And that's a very complicated problem. It's actually NP-complete, demonstratively. So what would be cool would be to be able to call the function C directly and verify if there is a problem. So that's what we're going to do. If we look at all the functions that are available right now, there's all of that. That's basically all the functions that exist either in shared libraries or in the main library proftpd. Okay, so I can call all of that directly for my shell. So I'm going to create a small variable, and we said PR underscore, what was it? Version what?
Version getString.
I don't remember. Let's link. Okay, function of PR underscore version what?
Version gets and then string str.
The second one, was that right? Yeah, okay. So I'm going to create a variable A in Lua, and I'm going to call version get string from proftpd. Okay, that worked. And if I printf in C, for instance, %s, that's the result of a function I called from within proftpd. And this is proftpd 1.3.5.e, which incidentally is correct. Doing this is super amazing and difficult. How do you think about it? Can you please show me back my slides? Thanks for your attention. Any question today? It was too easy? Thanks for your participation.